Let's do some examples. Let's do your homework on extreme value theorem. So we're going to be looking for maximums and minimums. We're going to make a sketch. I want you to be able to picture everything, which really makes your life easier and know. It should help you know what you need to write down, or at least where we're going. We're going to use our calculator. You're not going to see me do that. That'll be off screen, but I'll show you what you need to write down. And, well, making sure to write proper calculator work. So we're definitely not going to label A, B, C, D, E in the work, but we will be doing all of those parts. Ideally, you won't have to look. Okay, so maximums and minimums. What does e to the x look like? E to the x wouldn't normally have a maximum or a minimum, but we're given the closed interval -1 to 3, so we can use the extreme value theorem. And that's the first thing we need to write down. Sorry, I'm just trying to rearrange here. Y equals e to the x is continuous on the closed interval -1 to 3. So a maximum and minimum are guaranteed. That looks like one word. Let's change e to the x to look like e to the power x. Okay, and where do those maximums and minimums occur? At critical values. So y prime equals e to the x. The derivative of e to the x is e to the x natural log of e. And we can just go ahead and say y prime is never equal to 0, and y prime is always defined. So no critical values, which means the maximum and minimum will only occur at endpoints, which we kind of knew already. So because we know that, well, e is about 2.71, and these aren't even close, we could write 1 over e and e cubed and be done with it. Or we could put those into a calculator, which I'm not going to bother doing. Now, it feels like we're done, but we actually want to write an answer. So I don't think I wrote instructions very well, did I? Well, I guess. In green I did. Okay, so maybe right here we should say no critical values. And then y equals e to on -1 to 3, because that's the only reason we get a maximum and a minimum. Y equals e to the x has a maximum of e cubed, which occurs at x equals 3, and a minimum of 1 over e, which occurs at x equals -1. Okay, moving on to the next one. So sine of x would always have maximums and minimums, but we couldn't use the extreme value theorem unless we were given a continuous function on a closed interval, which we are. So y equals, and so, well, we kind of already know what we're going to get. A maximum of 1, a minimum of 0. But our job is to show the extreme value theorem part. So y equals sine of x is continuous on 0 to pi. We don't have to explain why. So a maximum and minimum are guaranteed. Okay, so we need to find some critical values. Y prime is cosine of x. We're going to let y prime equal 0. Y prime is always defined. and 0 equals cosine of x. So we get infinitely many results, but on 0 to pi, where's cosine equal to 0? Just at x equals pi halves. We would also have 3 pi halves, negative pi halves, but we only care about 0 to pi. So we need a table of values. So that's going to be the endpoints, 0 and pi, as well as the critical value, pi halves. And we're supposed to label, so we'll say critical value. Okay, and we're putting these into sine of x. Sine of 0 is 0, sine of pi is 0, and sine of pi halves is 1. Oh, I kind of ran out of room. Should have planned better. Okay, so the maximum of sine x on 0 pi is 1, which occurs at x equals pi halves. And the minimum is 0, which occurs at x equals 0 and at x equals pi. Cool. All right, let's start farther to the left here. What does the absolute value of x look like? Absolute value of x. Ooh, did I label these other ones? I don't think I did. Let's go back and do those. And maybe we should highlight the part we're looking at. Okay, so on -1 to 2, there we go. Okay, back to blue. So we can clearly see, we know the absolute value of x is continuous on -1 to 2. So a maximum and minimum are guaranteed. My pen seems to be going slow. Okay. So critical values. All right, secret time. The absolute value of x is equal to x when x is greater than or equal to 0, and negative x when x is less than 0. So y prime is equal to 1 when x is greater than 0. Y prime is equal to -1 when x is less than 0. And y prime is undefined when x is equal to 0. We're not asked about differentiability, so we don't have to prove that. We do need to state maybe y prime is undefined for x equals 0, which is the only critical value. Cool. All right, so we need a table of values, x. What are we going to put in there? -1, 2, as well as 0. And hopefully those are easy y values for us to figure out without a calculator. I don't know what that was. Okay, so we're nearly done. The maximum of the absolute value of x on -1 to 2 is 2, which occurs, how about an r? At x equals 2, and the minimum is 0, which occurs at x equals 0. I bet that one's the one people need the most help on. Okay, what about 1 over x squared on negative 1 to 3? Ooh, I like this example. Now, you might be thinking you don't know what this graph looks like, but we can figure that out. So I guess, first of all, pretty obviously, x is not equal to 0, which means our task at hand is going to be easy, because 0 is between negative 1 and 3, and 1 over x squared is discontinuous at x equals 0. But how would we find out the graph? Well, negative 1 squared is 1. 1 divided by 1 is 1. 1 squared is 1. 1 divided by 1 is 1. 2 squared is 2. And 1 over 4 is 1/4. 3 squared is 3. 1 over 9 is 1/9. And so we get a graph that looks like this. Okay? 1 y equals 1 over x squared is discontinuous. We need to be more specific. At x equals 0. So a maximum and minimum are not guaranteed. Which means, as far as extreme value theorem goes, we are done with that problem. I don't know why I opened this. Ah! Something's wrong with the computer here. Close that. Okay. Will x squared minus 8x have a maximum and minimum? Sure. Let's see, x squared minus 8x, negative 1 to 10, okay. Has a 0 at 0, has another 0 at 8. 10 is over here, and we're expecting a parabola. Negative 1 here. So I'm expecting the minimum to be at x equals 4. Just kind of using pre-calculus stuff, and the maximum to be at x equals 10. So y equals x squared minus 8x, we're kind of getting bored with this, is continuous on negative 1 to 10. So a maximum and minimum are guaranteed. You are writing the word maximum every time, right? Okay, we're going to look for critical values. Oh yeah, we didn't need to label that on the last one. We didn't get to the critical value point. That's what I was looking for. Okay, y prime is equal to 2x minus 8. Let y prime equal 0. Y prime is always defined. Zero equals 2x minus 8, and x is equal to 4, just like we expected. So we actually don't have to make a table of values. I just think it's the most compact, efficient way to go. Maybe if any of these are named f, we'll do that another way. And no, I made sure you used a table of values by giving you y equals every time. Okay, so I think it's best to go left to right. We really haven't gotten to a calculator one, so whatever. You know, you should not be using a calculator on these if you don't have to. I think it'll just slow us down. So maybe on this one we'll need to, but I don't think so. Okay, so negative 1 squared minus 8 times negative 1 is 9. 4 squared minus 8 times 4 is going to be 16 minus 32, negative 16. And 100 minus 80 is 20. All right, time for a conclusion. On negative 1 to 10, y equals x squared minus 8x has a maximum of 20 at x equals 10 and a minimum of negative 16 at x equals 4. Do we need to do more? Maybe just one more. Okay, so starting off, x cannot be equal to 1. But 1 is not on the interval 3 to 6, so I think we're good to go. I assume the next one, yeah, kind of the same function, but x equals 1 is on this interval, so number 7, you don't really have to do all of the mean extreme value theorem work. Okay. So, what does this graph look like? Well, this graph has a y value of 0 at x equals 0, has a vertical asymptote at x equals 1. End behavior, the end behavior's slant asymptote. Okay, let's see what's that slant asymptote. So x minus 1 into x squared plus 0x plus 0. And then that's 0 minus x plus 0, and that goes in 1. Okay, so the asymptote is x plus 1. Oh man, I did not leave myself enough room. Darn it. Okay. Okay, so put everything back. And then, there are kind of two choices. It's going to be just based on rational functions, one of these two bits, and which one are we going to keep? Well, let's think about what happens. Maybe at x equals 2 would be the best spot. 2 squared is 4, over 4 minus 1 is 3. That's going to be up here 4/3. And we can also see we also knew about that graph was equal to 0 at 0. Okay, so on 3 to 6, this graph is definitely continuous. I didn't finish my division, but I don't really want a remainder. Let's get rid of that. Okay, so y equals x squared over x minus 1 is continuous on the closed interval 3 to 6, so a maximum and minimum are guaranteed. And let's see. I suppose you could have been graphing these with a calculator, but if you have to use your calculator to graph, that would kind of be a problem for most of these. Maybe use it to check. Okay, so we need a derivative. We can't do much fancy algebra to simplify things ahead of time, so we'll just do the derivative of a quotient of two functions. And notice we don't have to worry about y prime being undefined on 3 to 6, so I think that's how we're going to phrase it. Let's simplify just a little bit. So that's going to be 2x squared minus 2x minus x squared. Still over x minus 1 squared. Even though we're ignoring that denominator, we still need to write it. I should be writing smaller. So we're going to What is going on, Mr. Penn? Technology. Okay. Let's try that again. Let y prime equal 0. Y prime is defined for 3 to 6. So 0 equals x squared minus 2x, and x equals 0, x equals 2 are the critical values. So for some reason my computer's giving up on writing, so I think I'm going to give up on this recording.